Hello students, welcome back. We just completed section 4 and now let's go to section 5, product and series of primes. First, let's discuss some series of prime numbers. Prime harmonic series. It's Euler's theorem. There are many things done by Euler, so if you just look up Euler's theorem in Wikipedia, you won't be able to find out. So you have to type in Euler's prime harmonic series theorem or something like that. Basically, we are talking about this. So that's 1 over 2 plus 1/3 plus 1/5 plus 1/7 11. Okay, that's enough. That's what this theorem is all about. By the way, do you recall that the growth order of the nth prime is at the order of n log of n? Do you remember this? It comes from the prime number theorem, from Gauss-Legendre conjecture. The first form is this. The prime counting function is growing at the order of x over log of x, and it can be proved that that's equivalent to the nth prime is growing in the order of n log of n. Of course, we're not going to do that in this class, but it is well known. So if you consider that, then this thing here, okay, let me rewrite this thing here, is going to be growing in the order of n log of n. And of course, we cannot start from 1 because log of 1 is going to be 0. So let's start from a little bit bigger number. And the latter series diverges to infinity because of the integral test. You can prove that this integral, let's see, integral 2 to infinity 1 over x log of x dx is log of x so that's 2 to infinity. Yeah, I think this is the correct antiderivative. Please check. You can use the integration by substitution to prove it. So if we know the prime conjecture, I mean the prime number theorem by Adamar and Poussey, then you can use this to prove it. But Euler lived a lot before those people. So Euler's proof is far more ingenious, and that's something we're going to study. And for example, compare this. Some of prime numbers, one of our prime numbers go to infinity, while some of square number, one of our square numbers is bounded, is finite. That means this inequality and that equality suggest, in a sense, there are a lot more primes than square numbers. And square numbers are easy to locate. Just take squares and then you can find out how many increments the next one will come. But prime numbers are really difficult to find. And then after hitting some really large number, finding whether a given integer with digits, say 100 or so, is a prime or not, is a kind of problem that can be done theoretically, but it'll take kind of like lifetime of a universe to calculate, even with today's best computers. So prime numbers are hard to deal with, but according to this, there are a lot out there. And of course, if you use Gauss-Legendre conjecture or prime number theorem, then you'll have much shorter solution. Still, let's work those out using Euler's idea. First, let's begin with negating the conclusion. Suppose that this thing is finite, then the tail part will be something, but in the end, the tail part will go down to 0. The head part, nobody cares actually. Whether a series converges or not is determined by the tail part. The tail part will have to go down to 0. So if we start from sufficiently big number after k, then 1 over pm, that sum, has to be less than 1/2. Why 1/2? That'll become clear later on. And that's because this tail part has to go to 0. Now, define Q as a product of k primes in the head part of the series. You see, P1, P2, P3 up to Pk, and then this series is starting from k plus 1, right? So multiply all those problems in the head part, P1 through Pk, just like we did for the proof of infinitude of primes by Euclid. Remember that? We multiplied all those and then considered q plus 1 and then did some modular arithmetic. Remember that? We are doing something similar. Then we can see that no pi divides 1 plus nq. You see, q is congruent to 0 modulo pi. So the remainder is always 1. So pi does not divide this number, no matter what n is. N is arbitrary positive integer. And of course, I could have selected 0, by the way. 0, well, that too is 0, but let's keep positive. And yeah, simpler modular arithmetic. So what does it tell me? This 1 plus nq for any positive n will have a prime factorization, but the prime factorization will have big primes only. Small primes up to k, p1 through pk, do not appear here because none of them divides as 1 plus nq. So all the primes are coming from the tail part. So 1 plus nq is product of a bunch of primes where those indices are greater than k, and then powers are greater than 0. And I didn't put all those characters here. I'm going to soon run out of characters there. So I wrote like this. I hope you understand. Okay, that's what you got so far. And why are we considering this 1 plus nq and doing this modular arithmetic that we considered before? It's with the Euclid theorem on infinitude of primes. Well, okay, answer comes. Here's a key lemma. We claim this. The sum of 1 over nq, where n goes from 1 to infinity, is less than or equal to this expression here. And then, wait a minute, this thing here, the summation of 1 over pm, that should be less than 1/2, right? Look at this, which I just highlighted in blue. And then this one. That was the starting point, you see. Assume the series converged, then the tail part must go to 0. So after some k, that summation, the tail part is less than 1/2. That was the starting point. So if I put that here, then this entire thing is less than the geometric series 1/2 to the t power. And this is certainly finite. Not only that, we can use the geometric series formula. Starting from 1, so 1/2 divided by 1 minus 1/2. So if I multiply by 2 to both numerator and denominator, I'm gonna get 1. Let's multiply by 2. Yeah, that's right. So that's what you're gonna get. Of course, all those come when you prove this. And let's prove that. So how does that thing work? This thing to the t power, and then you see this is all the sum of 1 over pm, where pm is sufficiently big, and then t power. So multiply all those t times. So basically we have a bunch of 1 over p, and then multiplied t times. And then all those indices are big enough, bigger than k, and then powers must add up to t. That's because this is t power. So if I take t goes 1 to infinity, then powers adding up to t can be anything, because t can be anything from 1 to infinity. So it's sum of everything of this form. So as long as these primes are coming from ladder prime, kth prime or later, or bigger than kth prime, so k plus first prime or later. Now, on the other hand, if you look at the left-hand side, not everything, it's just a prime factorization of 1 plus nq. Only those are coming. Here, everything, here, selected few. So which is bigger? Each entry is positive. Here, everything. Here, selected few. So right-hand side is bigger. That's how you get the conclusion. The right-hand side is bigger. So once you have that, and then apply the original hypothesis, the tail part is less than 1/2, we can draw a contradiction like this. This thing is less than or equal to the geometric series, and then that's finite, all right? But then again, if you apply the integral test here, and this versus this integral, and the integral, we can calculate this integral. It is 1 over q log of 1 plus qx, where x is going from 1 to infinity. That's infinity. There goes a contradiction. This thing is infinity in one hand by the integral test, finite on the other hand. So there goes a contradiction. So the original assumption must be wrong. What is our original assumption? Well, we negated this conclusion, assumed it was finite, and then we got that. That assumption must be wrong. The sum is not finite, it is infinite. That's Euler's proof on prime harmonic series. And as a matter of fact, that kind of opened the door for the growth order of nth prime and so on. And then people started working on this prime conjecture, Gauss-Legendre conjecture, and so on. Okay, so much for prime harmonic series by Euler. And we're going to come back and discuss some other series and products in a separate video, maybe 2.